just did it, yeah, we just did delta V.
Alright, so these are the equations we're going to be using for this chapter. We're going to use a different version of them as well in a little while, but when it's constant velocity, this is one place for you guys to get screwed up. It is constant velocity if it says it's not accelerating, or constant velocity, you use just this equation. So if at any point, like if something's traveling and it starts traveling at constant velocity, for that part you use this equation. Does that kind of make sense? Alright, constant acceleration. These, how many of you guys are in calculus? Everyone? Those of you look happy about being in calculus. You're like, alright, these are actually all derived from calculus, or most of them are derived from calculus, and these should be little dots, not negative signs. There's not a negative sign in front of all these. Alright, so delta x is going to be what? Katie?
It's just changing displacement.
Or, yeah, displacement or distance. Either one of those, for the most part, one-dimensional. 1/2 final velocity plus initial velocity times time. And then delta x equals initial velocity times time plus 1/2 at squared. Final velocity equals initial velocity plus acceleration times time. And final velocity squared plus initial velocity squared equals 2 times the acceleration times the displacement. Those look hideous right now? Mildly hideous? You'll feel better shortly. Katie, did they look bad last year at the beginning of the year? So they were pretty easy by the end?
Yeah.
Yeah. You guys will, some of you guys will be like freaking out over this stuff for the next week or so, and by the time we get to reviewing it at Christmas, it'll be like, this was hard. I don't know if that's good or bad about the class, but alright. I'm going to leave this one dot to bother people. Is it going to bother anyone?
Yeah.
Good. I've been doing that all year now. You shouldn't have told me. Alright. Free fall is a specific kind of accelerated motion. So, motion when things are moving vertically by themselves through the air. So when I throw this up and down, that's free fall. It's free fall when it's going up and when it's coming down. Does that make sense? So it's not just something falling, it's something moving vertically through the air. So important things, acceleration is always negative 9.8 meters per second squared. It's represented by lowercase g. The nice thing about that is you always know acceleration in free fall problems. So if we're talking about something thrown up or down off a cliff, you know what the acceleration is. Down is going to be our negative direction, and up is going to be our positive direction. And we're going to ignore any area resistance for now. We'll kind of pick up area resistance later on in the year, but for right now. Alright, so free fall, like this diagram, what happens here? So the velocity increases by 9.8 meters per second every second. What happens to the distance it falls every second? It increases. So the longer it falls for, the larger the distance it goes every second. So if you dropped 2 stones, one stone 1 second after the other, what happened to the distance between them as they fell? Increase. So if they're following each other, they get further and further apart as they fall. Does that make sense? Right, 2 important notes here. These are going to be the things that mess you up. The velocity at the highest point in something's flight is 0. So if I toss this up, when it gets to the highest point, the velocity is 0 there. Is the acceleration 0? No. What would happen if the velocity and the acceleration were 0? It would stay there. Obviously not what happens. It'd be kind of cool if it did. But so the velocity is 0 at the highest point. The acceleration is not 0. What's the acceleration going to be? Negative 9.8 meters per second squared. And why is that negative, that 9.8 meters per second squared? Because it's going down. Gravity always pulls down toward the earth, so that's why I make it negative. So down is negative. Alright, when we talk about final velocity of an object hitting the ground, we mean the instant before it hits the ground. We're looking for the velocity it hits the ground with. So you don't say your final velocity when it hits the ground is 0. So if I drop this from here, final velocity was not 0. The final velocity we're looking for is when it's like 1/1000th of a millimeter above the ground. Does that kind of make sense? equations for free fall, these are the exact same equations as for acceleration, except, again, there's no negative signs here. Except we replace delta x with delta y since we're vertical now, instead of usually when we talk about just accelerated motion, it's going to be horizontal. And a has been replaced with g. That makes sense? And one thing I guarantee someone's going to do, because people do it every year, a lot of times you'll simplify, you'll do 1/2, 9.8, you'll be doing enough of these problems, you'll say, oh, that's 4.9. You'll be doing 2 times 9.8, that's 19.6. So a lot of times you'll be doing a problem, you'll just, instead of writing out 1/2 times 9.8, you'll write out just 4.9 in there. Somebody is going to switch those two. You're going to write 19.6 here or 4.9 here. Every year a lot of people do that. It's going to be Emma. She's going to be the first one. That's my prediction anyway. You'll leave half one this time. Last year there were people who like these books would get messed up and they'd always like put them back together, so they'd put them all back together nice and neat, and I'd like come back around and move one. And then I'd have to sit in class staring at the book.
There's a lot of OCD people in this class.
Alright, this is, another tricky thing about this question is the way it's worded. What is the gain in speed per second of a freely falling object?
Is it 9.8?
Yep, 9.8 meters per second, or 9.8 meters per second squared. Right, with what velocity does a dropped object hit the ground if it falls for 1 second? 9.8 meters per second. So if it has 1 second to accelerate, it accelerates to 9.8. An object is thrown upward with a velocity of 19.6 meters per second. How fast is it moving after 2 seconds? 0. How fast would it be moving after 4 seconds? Negative 19.6. So if you go up, and when you come back down to the same height, you're moving the same speed in the opposite direction. That'll be useful periodically. Alright, graphing motion. We're almost done. Alright, so when something's moving at constant velocity, it moves the same distance every second. So if we graph that, we get a straight line. Make sense, everybody? What's the velocity of this car? How many meters does it move every second? 10. What's the slope of this line? 10. The slope of the graph of a position versus time is the velocity of the object. Does that kind of make sense to everybody? Because it's rise over run, so it's rise is your displacement, your run is your time, so it's displacement over time, and you get velocity. Does that kind of make sense to everybody? And you get to calculus. You haven't done anything in calculus yet, have you? What have you guys done in calculus?
Ethics.
We're talking about respect a lot, so we're good with that.
We're far behind.
We read like the first 2 sentences of the graph.
I don't even think we got that far.
If we're graphing respect, then we're good.
It all makes sense.
The slope of respect is, what would the slope of respect be?
Equals love versus.
The slope of respect, actually. Yeah, I'll come up with something later. We'll just leave that there though.
It's not on the line.
How bad is your OCD right now?
He is so bad.
What's his action? He was like, oh.
Alright, is that better, Julius?
Yeah.
How there's just a reading.
That was just a random line. Here. And I've got spelling OCD people too. Alright, accelerated motion. So in this case, do we have constant velocity? No. Is the slope of our line constant? No. So when the slope of the line changes, what is there? Acceleration. So is this positive or negative acceleration? Is the slope of the line increasing or decreasing? Increasing. So the car is accelerating positively. If the slope of the line decreases, then it is slowing down. Does that make sense to everybody? Okay. Now we're going to do velocity versus time graphs. So, what's the slope of this line? 0. And it's obviously 10 meters per second for the velocity. What else is 0 in this situation? Acceleration. So what does the slope of velocity versus time graph represent? Acceleration. So slope of velocity versus time represents acceleration. And so if you have a non-flat line, what's the slope of this line? 4 meters per second. So, or 4 meters per second would be the slope of this line gives you the acceleration. Does that make sense to everybody? Okay. We're gonna backtrack here real quick. One other thing, this is not till you get to integration and calculus, but what does the area under this curve represent? What's the area of the square right here? Or it's not actually a square, but 10. So if we have that, 10. What else is 10? 10 meters.
It's a constant.
It's the displacement. The area under a velocity versus time graph gives you the displacement, how far it's gone. And you can think about it this way. What did you do to find this? 10. You did velocity times 1. So if we have velocity equals distance over time, we have distance equals velocity times time. So to find the area, you do velocity times time, so it equals distance. Does that make sense to everybody? I'll leave that there too. And you can do it with this, you have to use triangles and stuff like that. That's almost always a problem on the AP test. They'll give you a graph like this, and they'll say, find the displacement. Where it'll be like a triangle up, then a square, and then a triangle down. So you just find the area of that geometric figure, and you can get the displacement. Okay, this will be fun. This is more for your amusement than really to learn anything, but you'll learn a little bit. Alright, so we want to look at graphs. So you see this little guy, we're going to make him move. We'll start him over here, give him a velocity, and we'll make it a negative velocity. So he's going to be moving toward the negative direction. What's the graph of our position versus time going to look like? Since he's moving, there's 0 acceleration, so what's this graph going to look like, position versus time? And what's the velocity versus time going to look like? Straight line is 0 slope. I'm moving slow. You're into the wall.
Of course.
Alright. So now let's start him back. Well, let's start him back here. Let's give him a positive velocity and a little bit of a positive acceleration. What's the position versus time graph going to look like now? Curve upward. What's the velocity versus time graph going to look like? Upward slanted line. And here's the...
He misses the house, but he hits the wall.
The house is in the background.
Oh.
Anyway. Alright, now let's put him right here. Let's give him a, actually let's put him back here. Let's give him a positive velocity and a negative acceleration. There we go. What's going to happen now? He's going to go this way, or this way, slow down, turn around and go the other way. Does that make sense? What's the graph of position versus time gonna look like?
Curve down.
Down curve.
For how
Thing.
long?
Alright. So he started going this way initially. Right here, he turned around and went back this way. What was his velocity when he turned around? Like that instant he turned around? 0. So when the slope of this graph is 0, that's when he stopped and turned around. And to see how it lines up when the velocity crossed the 0 point in the axis there. Does that make sense to everybody? See how I line up? Alright. Now this is just because I get a kick out of this. But he's going so slow. I don't know why the computer's making him run slow. We'll just. Alright. So now let's move over here. Pause. Let's see how fast we can get him to go hitting the wall. I'm done now. Alright. That's how we want that. Alright. Do you guys kind of understand how the graphing works? Alright. So that goes to some questions here. Below are position versus time graphs for objects A and B. Which object has a larger speed? B. Why B? Steeper slope. What does the slope of a position versus time graph represent? Velocity. Okay. In which graph is there acceleration? Both. In which graph is there negative acceleration? B. What does it mean if the slope of a position versus time graph is changing? Acceleration. Okay, what's happening to the object in the first 5 seconds? Position versus time graph. Going at a constant velocity. What's happening in the second 5 seconds?
Standing still.
Stationary. Does that make sense to everybody? Alright. The graph on the right there is the object moving in the positive direction. Yes. Even though it's slowing down in the positive direction, but it's still moving in the positive direction. Does that make sense? Is the object speeding up? Just answer that. No. Is the object slowing down? Yes. Does the object change direction? No. Does the object have constant acceleration? Yes, so it is accelerating. When would it change direction if we continued this line? It went across the 0 point. Yep.
So if the velocity versus time graph is like curving, does that mean the acceleration is changing?
Yes. We're never going to deal with that in here. You can kind of keep graphing stuff. Eventually you have to have something that's a straight line. But and what would the area under this be? Displacement. What does the slope of a velocity versus time graph represent? Acceleration. Alright. One thing that's gonna come up again periodically on the AP test is vector and scalar quantities. You guys know what those are? Have we talked about those all before in any? Sort of. So vector quantity is something that has both magnitude and direction. Magnitude just means a number. So it has like velocity has the speed plus a direction, so the speed's a number plus a direction. Scalar quantity is something that has magnitude only. So speed is a scalar, it's just how fast you're going. There's no direction associated with it. So when you do a vector times a vector, you get a scalar. When you do a scalar times a scalar, you get a scalar. When you do a vector times a scalar, you get a vector, not a scalar. So it's kind of like negative signs to an extent, with a vector being negative. Alright, questions? Yeah.
So, you know, with the graph of, what was it, of choice, or which one was it? The velocity versus. Wait.
That one?
Yeah, if you graph acceleration versus time, then would the area under that be velocity, average
Yes.
velocity?
Yep. So it kind of like it keeps going kind of backward, like the opposite, the area under the curve and the slope. Any other questions? And when you get to calculus, you'll be calculating the area under the curve and the slope here. When you do derivatives, you do the slope. When you do integrals, you do the area under the curve. All right. Any other questions?